Welcome back to the Quantum State. Today, we're joined by Marcus Doherty, co-founder and chief science officer of Quantum Brilliance, one of the few companies pioneering room temperature quantum computing using synthetic diamonds. So room temperature has always had its own challenges, but now companies like Quantum Brilliance are moving forward to deployment in the real world. And that's what we're going to discuss today. So welcome to the show.
Hey, Anastasia, Gavin, it's my absolute pleasure to be here. Looking forward to the chat.
Yes, and Marcus, please tell us a little bit about yourself and what led you to founding Quantum Brilliance.
Yeah, so I've been developing quantum technologies for over 20 years, and it's always been related to defects in semiconductors like diamond. And I started off in a startup company called Quantum Communications Victoria back in the early 2000s, which was building some of the world's first single photon sources. And that was a really formative experience being in a young startup company. And then after that, moved on and ultimately got sold. I went into an academic career where I then focused on diamond quantum technologies. And that then led me to Quantum Brilliance in 2019 when we founded it. And it was one of those moments where myself and Jörg Ruchtrup, who's a professor in Germany, we were sitting in an airport lounge and we were lamenting that, hey, the promise that diamond quantum computing had was always to be the quantum laptop, this idea that we can make these miniaturized, portable, but still useful quantum computers. And that was the vision that York had when he first proposed diamond quantum computing in 2001. But there was a problem, which was actually how to scale up the number of qubits and how to manufacture to create that vision of a laptop.
Yeah, so that's interesting. So you went kind of the opposite way. You went from a startup to academia. And a lot of people did the whole academia path first and then it went into startups, and you kind of completed more of a loop there.
Yeah. So it's I look back at it in hindsight and go, wow, that sort of set me up for my, I guess, a different attitude or a different approach to thinking about now spinning technology out. But at the time, it didn't feel like that. It just felt a natural way of doing things.
Definitely. Yeah, when I was back in my undergrad, I was looking to go into grad school actually, and V Centers, I toured Ron Walsworth's group back in the day, and thought that was maybe one of the research paths I wanted to do. And definitely still early. That was more than a decade ago now. So a lot has happened since. So let's really just start with the fundamentals here. For listeners who might not be familiar, what exactly is quantum brilliance's core technology? What makes these nitrogen vacancy centers and diamonds such a promising platform for room temperature quantum computing?
Yeah. So from that airport lounge conversation with Jorg, what we identified was um, what we needed to do is really focus on how to design and fabricate and ultimately manufacture integrated chips with diamond, and in particular, the nitrogen vacancy centers, which are the qubits that we used in our computing technology. And so that's what I did at ANU, was I really focused on how to fabricate these NV centers with the precision and the yield that could one day be able to make sort of microchips of large complexity. So that was the work I did at ANU, and then ultimately that then led to the core technology that spat out and create Quantum Brilliance. So we are an integrated quantum chip company. That's the way we think about ourselves. We develop fabrication tools and processes and designs to make these integrated chips. That's the core enabler to be able to firstly arrange these NV centers in a way where they interact so that you can create scalable maps or connections of these qubits together. And then also to be able to fabricate that thing so that you can actually use it in real life.
Can you tell us a bit about the computational model for these nitrogen vacancies? Is it gate based, adiabatic? What is the model you use? What kind of universal gates can you get?
Yeah, so the end state that we're aiming for in 2030 is a gate-based quantum computer. So let me talk a little bit more about the technology. So at its core, a diamond quantum computer contains an array of NV centers. These NV centers are spaced about 5 nanometers apart, and they're in some sort of two-dimensional configuration. Maybe it's a hexagonal lattice or a square lattice. The way they interact with each other is a direct magnetic interaction. So the NV centers have a spin, which is a magnetic moment, and these produce a magnetic field, and one field then interacts with the moment of another NV center, and so on. So that's the core layout. And the way that you control these NV centers is you use light and electronics to initialize and read out these NVs. And you use microwaves to control their state. And that combined with that magnetic coupling gives you a universal gate set. So you can do individual single qubit rotations using your microwaves, and then that interaction then allows you to do control operations between different NV centers in that array. So to summarize, it's nearest neighbor 2D lattice of qubits. Where we've become quite interested, though, is that as we mature the fabrication technology and as we seek to scale up the number of qubits, we don't necessarily need to have full control to make something that is potentially useful. And that's where we're becoming interested in analog devices, such as more towards things like reservoir computing, about embedding machine learning problems as an accelerator to a larger classical machine learning workflow. And then perhaps in the more distant future, with the fully controllable gate-based quantum computer, then having something that can support quantum machine learning.
Okay. And is the information stored in nuclear spins or electron spins?
Yeah, so the information is stored in the nuclear spin, so that associated with the nitrogen, which comes with each NV center. And the electron spins are then what mediate that interaction, that then enables you to do those controlled gate operations between the nuclear spins of different NV centers.
Great. And can you tell us a little bit about the current benchmarks? Like, how many qubits do you have now, and what are the rough quality of the gates?
Yeah, so in our production devices, so these are the ones that we sort of manufacture and ship today, which are these really early prototypes, which whose purpose really is to prove that you can box up and deploy quantum computers and enable different computing architectures, and I'll come back to that later. We're at 2 qubits, and we have fidelities above single qubit fidelities above 99%. We have initialization and readout fidelities above 99%. On 2 qubit fidelities, we've got a bit of work to do. But what gives us confidence in laboratory systems, so benchtop systems, you can get above 99.9% in the 2 qubit fidelities. So that's already been demonstrated. And indeed, guys in the Netherlands have done 50 qubits with NV centers, although they did that at cryogenic temperatures. So there's no fundamental paths or blockers here to achieving higher fidelities. It's really is an engineering problem, and that's part of learning what it means to package up and integrate components together, and how do you then do that in a way that enables you to achieve high fidelities.
Yeah, on that, can you elaborate a bit? You mentioned that the benchtop systems have high fidelities. What's the difference between that one and yours? And obviously, we're going to get into the cryogenics and everything later, but what's the difference between their capabilities and what you guys are trying to do in terms of deployment?
Yeah, so look, the main difference is that in a benchtop system, your optical, electrical, and magnetic systems are all distant from each other, right? And then when you come to then integrate and package a device, you then have to bring all of them closer to each other, and there is, interference that occurs between those different control systems, which you then have to work through as you're miniaturizing and integrating your device. And so we're on that journey at the moment, but not something that has never been solved. It's real classical engineering, right? And so it's a well-tread path, and so that's what we're on. The And so I think the other thing when you package up a device is that you take it into a very different environment and world. So the devices we've deployed into high performance computing centers, these can be incredibly hot and noisy environments, depending on what sort of infrastructure you're deploying into. And so as a result, you've got to engineer your system to be able to operate in those sort of what can be fairly extreme environments.
Yeah, that's super interesting because you kind of have the two pathways in some way of when someone's looking outside, and because a lot of our listeners are investors and people who are less scientists in the field as well, right? They look at these numbers and they go, "Oh, these low percentage, it must be terrible." But then you go, "Well, yes, like we can do the high thing, but here's all the other issues to actually that thing won't actually make it to deployment, and here's the path we're doing. So it looks worse, but actually this is the path that we need to take to get it to deployment." So that's really interesting that you have to kind of balance that within the business and within your organization to kind of make people outside of the space understand what you're trying to do. And so with that packaging and kind of scalability, obviously this how does the room temperature systems and the packaging change the economics and accessibility of quantum computing? And with this, I'm not sure if you saw the ICM report. I keep bringing it up because I keep thinking about a lot about, all this technology that the cryogenics cost a lot. Trapped ions cost a lot. There's a lot of peripheral control hardware that costs a lot that you still need to integrate to make these systems deployed. How does room temperature kind of change the economics of quantum technology? What's kind of the priciest bit of your technology?
Yeah, gotcha. So, uh, as you're saying, we're going in a slightly different direction and with a different emphasis, which is our vision really is to make GPU-sized quantum computers, which you can manufacture at the scale of GPU manufacture today. And so it leads to quite a different, and I would say bigger picture for quantum computing than potentially the more limited picture that other quantum computing platforms offer. And that also is why we are focusing on different things. We're not rushing to scale up qubits because that is not necessarily the core part of our value proposition. We also have to address these issues about miniaturization and manufacturability in order to deliver that end future, and to deliver the value of our technology. So our core technology is all about computational power density. So it's about giving people the opportunity to have a step change in how much computing power they can integrate into something, whether that's a satellite, whether it's a vehicle, or whether it's thousands of quantum computers working together in a data center or a high performance computing center. And so the economics look very different. And that is that for someone to buy our computer, and if it's the size of a GPU, it only needs to outperform a GPU, one GPU, not 1,000 GPUs. And it needs to cost somewhere equivalent to a GPU. So that's quite different to other quantum computing technologies where they have to outperform clusters of GPUs, and also then be comparable in size, weight, and cost, and power consumption compared to those clusters of GPUs. And so as a result, whilst I see it two different tracks, us going after outperforming a single GPU and facing the miniaturization manufacturing challenges, the other computing technologies going after supercomputers and facing all the challenges it means to compete against a supercomputer. And what I mean by a bigger future is that I don't necessarily see our technology competing with many other quantum computing technologies. I think they are complementary. I see most other quantum computing technologies as the mainframe computers of the future. So they're the things that you use for very difficult tasks, but only a few of those tasks. Our computers are the ones that you use for less difficult tasks, but where you have many tasks that you have to complete within a smaller amount of time. And so ours look more like a data center, and those other computing systems look more like mainframe computers that we've seen in the past.
Yeah, just to follow up on that, it's interesting. People are starting to talk a lot more about module sizes for quantum computers now, like the neutral atoms, could feasibly get tens of thousands. Superconducting seems to be limited to, a couple thousand qubits. Ion traps have issues with, you can't have too many in a zone, interaction zone. Um, and so if you really want to scale up to big problems, you have to think about optical interconnects and so forth, or shuttling physically qubits around between modules. How does it work with your kind of system?
Yeah, so scaling up is fundamentally about enlarging that two-dimensional array. So much like most other sorts of semiconductor-based quantum computing. Um, then so scaling a single array will get you to about 100 physical qubits. And then there's limitations in then the physics of the control of those arrays that then you have to change to a different architecture. And so I won't necessarily talk about the details of that different architecture, but you can imagine going to something like a superlattice where you now have several arrays which are connected at edges. And then that enables you to scale beyond that 100 qubits to, in principle, unlimited number of qubits in a single diamond. So there's one advantage, which is, hey, we're working at the nanoscopic scale for our qubits. And so in an ideal world, you could fit millions or billions of these qubits on a single diamond. Like the transistor in silicon, that however brings the need for very mature fabrication technologies. And so to be able to actually engineer that thing and make it, as compared to other technologies where they can rely on less difficult or existing manufacturing techniques to scale quickly in number of qubits, but then also face challenges about ultimately how do they miniaturize and then adapt to those other integration challenges and things that I've described.
So you mentioned a little bit about machine learning and how your approach differs from some of the other players, but machine learning tends to be an application people think about a little bit for the longer term. Are you looking at other kinds of problems in the meantime?
Yeah, so I mentioned, um, uh, so I sort of see taking us as a chip company. I really see us releasing chips of escalating complexity over the next 10, 20 years, right? And in the next couple of years, releasing chips which are quite low complexity. So these are quantum sensing chips, and then also early analog devices for quantum computing. And so one of those examples of a use case of an analog device is for that reservoir computing for embedding, for data embedding, for classical machine learning. The reason why that's interesting is that, firstly, quantum sensing has a terrific number of important applications, right? And I think people are only really starting to realize the value of quantum sensing. But if we're focusing on quantum computing, is that if you genuinely can have a chip scale solution, then it enables people to ingest and design in quantum computing in a way that you just can't otherwise. And so these early analog devices will be like the early analog devices that came out of the silicon transistor technology of the 1960s, which then led to calculators and these other sorts of things. So whilst the longer term vision of 2030 is to have a 64 physical qubit chip scale solution that could in principle begin to do interesting quantum machine learning. Between now and 2030, it's really then about sensors and early analog devices of potentially still around the 1060s of qubits, but maybe not fully controllable in every aspect. Beyond 2030 is then when we are looking to scale towards a fault-tolerant chip. And so 2035 is then when we're seeking to have 64 logical qubits in a chip scale solution. And so that sort of gives you how we're thinking about things. Quantum machine learning is kind of the flagship application that we have in mind when we're thinking both the analog and then the NISQ era, and then fault-tolerant quantum computing, the more distant era for us is then, you know, the broader set of types of applications.
Yeah, so something that's very unique about Quantum Brilliance, certainly that always, you know, captures the attention, is that you're doing things at room temperature. But then, you know, that you typically run into issues with decoherence. Hotter environments cause more dephasing and so forth. Can you comment about how you're able to actually mediate against noise induced by a hot environment, and what kind of control techniques do you use to stabilize your qubits?
Yeah, so the wonder of diamond quantum technology is that we do have this exceptionally long coherence at room temperature. So at room temperature, our qubit coherence times are tens of milliseconds, which is, you know, 1,000 times longer than superconducting qubits, and converging on what the atomic technologies give you in terms of coherence times. The reason for that, speaking very simply, is that the main cause for decoherence for spin systems like NV centers and diamond, and also other semiconductor spins, is typically the interaction between the qubit and vibrations in the crystal. Diamond is so exceptionally hard that even at room temperature, there's not enough thermal energy in the environment to create large numbers of phonons or vibrations in the crystal. And so that, combined with an intrinsic low coupling between the qubit and the lattice called spin phonon coupling, means that you have these exceptionally long coherence times at room temperature. So that's the sort of fundamental physics reason. The real question isn't the coherence time though. The real question is, how do we initialize and read out at room temperature? And that is due to this intrinsic physics of the NV center, this optical cycle that enables you to optically pump and cool the spin to an effective temperature, which is on the millikelvin scale. So we essentially do optical cooling in order to initialize our qubits. And readout then is the opposite, which is, hey, the emissions of electrons and holes and photons from the NV center depends on the spin state. And that's how we can read out at room temperature. And that is strange. So there's virtually no other semiconductor system that allows you to initialize and read out at 99% fidelity at room temperature. So that's the weird thing, I think, about our qubit technology, not necessarily the coherence stuff.
Right. Yeah, it really, you know, emphasizes the point that when we say temperature, you have to be specific about temperature with respect to what degrees of freedom, and you know, how you can reduce the entropy of certain degrees of freedom, like your spin degrees, efficiently.
So going back to the deployment, I think you were talking about, you know, a lot of this theoretical stuff you're working on, but you actually recently deployed in the Fraunhofer Institute for Applied Solid-State Physics. So you already mentioned a little bit, you're really focusing on being deployed in the data centers. So are you planning on miniaturizing it more, or are you looking at just staying in that, continuing to increase computational power with the workloads that you're doing there?
Yeah, so what we've deployed to Fraunhofer and what we're deploying to Oak Ridge National Labs is a 19-in-track unit that contains about the size of a cabin buggy luggage that you take on the airplane. What is contained in there is the QPU, which is this 2-qubit system, but also a GPU and a CPU. And so and these are connected through PCI buses. And so this is a deeply hybrid system, right? what we are delivering to Oak Ridge National Labs is a cluster of 3 of those units. And then those units are then connected together through a normal sort of communication channel. And that then enables parallelization. And so the sorts of things that are going on at IAF and at Oak Ridge is using that as a platform to investigate hybrid and parallel computing. And what does it mean to do that? And how is it useful? And then what is then the design of that computing architecture? What does memory look like? What does communication look like? What workloads do you distribute asynchronously to these different processing units? And how do you get them to work together? So that's the set of questions that our current machines are designed to answer. Now, in terms of the future, yes, 2030, our goal is to have that GPU-sized device. And there's 2 ingredients to that. There's the really hard bit, which is taking what we currently have as diamond and optics and electronics and turning it into a packaged integrated device. And so that's the work that we're doing as part of our company in Germany, working within the semiconductor ecosystem of Europe in order to do that. The other part, which is, easier, is taking the classical electronics and turning it into a motherboard. And so that's the other core ingredient. So those 2 things together, it's making a chip and taking a box and turning it into a single board motherboard. They're the 2 big directions that we're taking towards the miniaturization. As we scale up to the qubit numbers I mentioned earlier, which is 2030, 64 physical qubits, 2035, 64 logical qubits.
You mentioned hybrid workloads. Do you have any sense of what specific problems they're going to be solving?
Yeah, so an example of the work that we're doing at Oak Ridge is thinking about molecular dynamics. So in molecular dynamics, a lot of problems are systems of many interacting molecules, right? And those molecules generally follow classical trajectories, and they have moments of chemistry, right? And so there's a well-established technique called QMMM, which is quantum mechanics. What's MM for? Molecular mechanics. And the molecular mechanics is handled by classical computers, and the quantum mechanics used to be handled by things like DFT calculations, so quantum mechanical calculations on classical computers. So what we're exploring is, can we take that quantum mechanical part of that simulation and give it to an actual quantum computer and handle not just one molecule, but multiple molecules. So we have multiple classical computers doing the classical trajectories and forces, and we have multiple quantum computers, which are then handling those moments of chemistry. So that's an example of one of the applications that those devices are supporting exploration in.
So Quantum Brilliance has announced partnerships with defense and aerospace groups like the Australian Department of Defense. What are the near-term applications where your tech is already being deployed or piloted?
Yeah, so I think that the nearest term applications in quantum sensing. And so where we sit in quantum sensing is really being that partner that enables high performant chip components and pathway to manufacturability for those people who are already building quantum sensors. So there's lots of companies, there's about 40 odd companies worldwide building diamond quantum sensors. And we can be that partner who works with them to deliver the chip and manufacturability technologies that enable them to accelerate their sensor product development and also actually deliver on what sensors need to be, which you need thousands and tens of thousands or millions of these things to make them work. Example use cases are GPS denied navigation. So diamond magnetometers are one of the competing technologies to perform magnetic positioning. So this is where you measure the Earth's magnetic field locally and you compare it against a magnetic map. And by comparing, you can make an estimate of where you are in the world against that map. And so NVs is one of the technologies that can offer those sorts of magnetometers. And so we're working with companies who are already doing that magnetic navigation with NV sensors, and we're providing a pathway to higher performance sensors in their manufacturing. Other examples is we've done work with Lockheed Martin in the past where we looked at quantum machine learning for synthetic aperture radar. So there are satellites that orbit the Earth, and these are constantly picking up radio signals from the ground. And by collecting and interpreting those radio signals, you can perform a radar image of what's on the Earth's surface. Let's say it's a ship on the ocean. The challenge is that you then have this quite constrained communication channel back to Earth. And so as a result, all that data has to be collected, and then all of it has to be transmitted back to Earth to then be processed to to identify from those radar images what ship it is on the ocean. And so the problem that Lockheed was seeking to solve is, do our quantum computers offer that change in computing power density that would enable them to do that on satellite and not have to transmit all the data back to Earth? And most specifically out of that, forming quantum machine learning to do that inferencing bit of feature detection and classification of, let's say, radar images of ships on the ocean surface. So that was an example of an application that was very specific to this idea of compact deployable quantum computers.
Is there also applications for electric field sensing with NVs?
Yeah, so you can certainly do electric field sensing with NVs. I think taking that in one direction, you can do things like monitoring electric vehicle batteries, and so there's wonderful work that's going on in Japan about using NVs to monitor charging and discharging within these very high capacity batteries. I think the real value in electric field sensing of NVs is actually what I call microsensing. So this is detecting things at very small length scales. And so there was work that even I was involved in, which was around using these things to detect neural signals. And so there's a wonderful company in Australia called Chromos, which is a spin out of University of Melbourne, which is seeking to make these neurosensing chips to enable the development of neuromedicines. So a challenge in development of neuromedicines is having sufficient access to sufficient scales of brain models and sensors that can detect sufficient information about what's happening inside those brain models for when you're experimenting with different doses or different types of medicines. And so as a result, the development of neuromedicines is quite constrained and slow because you can't scale your experimentation. So Chromos is seeking to provide that solution, which is a scalable sensor that is compatible with brain model tissue, which could then provide that platform for scalable development of neuromedicine.
Interesting. All right. So something else, I believe you're working with IMEC on integrating diamond qubits into CMOS fabs. What are the technical roadblocks for achieving CMOS capability?
Yeah, so we're seeking to work with IMEC on how to scale up some of the core manufacturing elements of making these integrated chips. So that is things like metallization on diamond. How can you do that at larger scales to enable greater throughput and a pathway to manufacturing, and also acceleration of research and development?
So, can you tell us now a little bit more about what your commercial roadmap looks like in the next year or two? I mean, you have these new partnerships that you've established, other research that you're doing. Are you focusing more on kind of working through those existing challenges with the partners you have, adding additional partnerships? I also noticed you all released the VQPU, I believe, that seems a little bit more dev focused. What's your plan?
So our plan over the next few years is to firstly demonstrate our core technologies. So we've been working on these for a while now, and we've made really significant progress. So this is being able to demonstrate all of the key ingredients to be able to make scalable computers and also scalable manufacturing of sensors. And so those technical demonstrations will occur in the next 2 years, and so our target is a 10 qubit device next year, which has all of those ingredients to scale and it is on that path to chip scale. The other thing that we are doing is really concentrating on solving and identifying key application areas for those sensors and also those computing devices. And so VQPU is an example of a tool that enables us to work with people, or for people to just not work with us and just use it to explore and test applications for our quantum computers. So our current quantum computers, as well as our projected quantum computers in the future. So it's an emulator that allows people to try out the performance of our device. And so it includes real models and characterization of the performance of our current device and projected future devices. So that's what the VQPU enables. So we're going to be doing more of that, and it's going to be along the areas that I've already described, where we sort of had this initial focus on machine learning, initially in analog devices, and then in NISQ digital devices, and then eventually in fault-tolerant devices. Another key element of what we are doing is we're building this diamond foundry in Australia. So a key element to diamond quantum technologies is to be able to scale up access to diamond material. And so that foundry in Melbourne, it's really about working with existing production partners around the world to accelerate the production of quantum grade diamond. And so it's about doing work about developing new processes, new metrology tools that can be translated to these production partners that enables the scalable access to quantum diamond. That's necessary for our chips, but it's also necessary for our quantum sensing partners to have access to those materials at scale, to scale their quantum sensors into the markets that they have over the next few years. So yes, those core technology developments, those core use case and value proposition validation around our sensing and computing applications, and addressing some of those important supply chain challenges around bringing diamond quantum technology to market.
I was also curious about whether you've thought about entering the communications space. So NV centers and diamond have been demonstrated to be useful for quantum memories. So things, like making quantum networks for Bell state distribution over long distances, that kind of thing. Does Quantum Brilliance have any interest in that kind of commercial activity?
Yeah, so hey, diamond quantum communications is a thing. The work out of TU Delft and QTech, where they did, the world's first loophole-free Bell test by having distant quantum registers connected by a light, and also LightSync, notably a spin out in the US that was acquired by IonQ. That was a diamond quantum communications company that was acquired by IonQ. So yes, diamond quantum communications is a real thing. We would see ourselves more as providing fabrication processes for communication technology rather than being a communications company. So there might be a real future where people like LightSync or people like QTech come to us and ask us to fabricate various components of their communication devices.
Yeah, so are you seeing any sort of I'm really interested in this entire ecosystem, right? Because it seems like no one's really manufactured this at scale before, so you're also solving that challenge. Are there any supply chain hurdles you're solving for to scale this manufacturing?
So the primary one is diamond. right? So diamond historically has been a material used for its hardness and its thermal properties. Um, you know, the later half of the 20th century, its optical properties. And now in the 21st century, beginning to be used for its electronic properties and now quantum properties. And so it's a material that's coming on the journey from being a mechanical material to a semiconductor material. And so um, that's the primary challenge, which is to get it to where other semiconductor materials are at today. But it's not a weird path. It's a path that gallium nitride has recently gone. So, which is now the core to, and silicon carbide, which is now core to the electric vehicle revolution, right? And so we're seeking to follow the same steps and bring diamond to as a semiconductor material. That's the platform that then enables a lot of other things to shake out. I mentioned working with foundry partners to transfer processes on existing tools to then onto diamond to then enable that fabrication scale up to occur. So that's another key aspect to this. But all of this works when there is clear demand and use cases for these technologies, and people know how to work together. So people know what they need to deliver to meet that demand. And so that's kind of the behind the scenes work that Quantum Brilliance is seeking to do as in the industry.
Yeah, and you mentioned a lot of these partnerships are with the data centers themselves. Um, are you seeing what are the trade-offs you guys are thinking about in terms of deploying quantum systems directly to the customer on premises versus having access in the cloud? Do you see people leaning one way or another? Does it matter by the industry? How do people think about quantum technologies?
Yeah, so by far the customers who want on-premises quantum computers are those subset of high-performance computing centers who really want to be part of pioneering the use of quantum computing. So uh, these are the ones who want to actively be part of the engineering and design of the future quantum computing in supercomputing. And so that's certainly the attitude that we've had when we've worked with Pawsey Supercomputing and IAF and Oak Ridge, is that they want to participate in trying to then engineer and architect that future for supercomputing. So that's really the the customer profile that is seeking on-prem. For many other customers, cloud-based services are completely fine, right? It gives them everything that they need. The other type of customer for us is where integrated and mobile devices is then king. So I talked about Lockheed Martin. So that's an example where the whole context there is about it being integrated into something. And so you have to address those questions alongside with playing around with the application to make sure that you can get to a conclusion to say, hey, this is actually valid. Not only can we computationally do something, but it's actually engineerable to be able to actually deploy and use that computational solution.
So, being in Australia, we think we have a pretty robust quantum ecosystem, but outside, sometimes Australia is not the first country people think of in terms of quantum technology, quantum computing. How do you view your position globally, especially as a quantum talent and capital cluster in the US, EU, and China?
Yeah, uh, uh, so Quantum Brilliance, span out of a university in Australia, but then always had its roots also in Germany. And so we are an Australian-German company. Half of our staff are in Australia and half of our staff are in Germany. And so from very early on in the company, we have always sort of seen ourselves as being global and not sort of a core Australian and only Australian company. I think that has been good. It's allowed us to participate and be genuinely a member of the European quantum community, whilst also being part of the Australian community. And that's and also enable us to see the differences between how those different places have undertook their quantum strategies, and how they've encouraged and developed the quantum industry. And there's very significant differences between the EU and Australia and how they've gone about doing that. But I think Australia is respected as a place where there is, significant quantum talent. I think what Australia has the challenge with is, we're not known for bringing things to market, right? And the questions immediately start about, well, how are you actually going to do that in Australia? And there are questions to answer. And so that's why Quantum Brilliance has always looked sort of globally about how do we best get the talent, the people, and the partners to actually do this. And so, yes, we're in Europe. We've recently opened office in Japan because Japan is another center of excellence in diamond generally, and also quantum diamond. With the Oak Ridge deployment, we're also now looking to the US. So yeah, I take a global picture to these things, and I think you have to as a quantum company.
Yeah, definitely. So you said you started in 2019 as well, is that correct? So that was also right before the world shut down, and so you've had to be global. So how do you attract and train talent that not only is dispersed but also needs to have experience across so many different fields? It's not just quantum challenges you need diamond people, you need embedded systems, data center people. How do you attracting people, sometimes it's fine. You say quantum, people want to work on that, but training them across all this knowledge, how do you do it?
Yeah, it's hard, and we haven't done it well, and then we've done it really well, and all these sorts of things, right? So, to be honest, this is the day-to-day inertia of building a quantum technology company. Is that you're bringing together people who have either never worked in an engineering context like physicists, or people who haven't worked in these explorative areas where you're generating fundamentally new technologies, like more traditional things like process engineering. And so as a result, you've got to work out how to make it work. And I dare say we're reinventing the wheel, but we kind of have to because we've got to go fast. And so we've got to do a bit of reinvention to balance speed versus accuracy. So yeah, it's one of those things that is the day-to-day effort in the company, is how do we work together better as people, and how do we bring these multiple disciplines together?
Is it harder to teach quantum people engineering or engineering people quantum?
So yeah, being one, I can say, which is the biggest problem with quantum is quantum physicists, and that the sooner there is less physicists in quantum, I think the better for the technology in general. It is hard to teach physicists engineering. Um, it's easier to teach engineers quantum. That's my experience. Now I say that lovingly because I am a physicist, and so you've got to take that with that spirit.
I have a similar joke. I was like, physicists are good coders, they're terrible software engineers. And that's why I spent 3 years doing algorithms and HPC coding, my real coding work, because I figured I should learn how to actually code in the correct way and production scale.
But you need those physicists who have that really deep knowledge, who can come up with those new inventions, right, of how to do it. And so it's more about the physicists bring extreme value, but that value needs to then have organized teams of engineers to then bring it to fruition. Yeah, so the biggest thing that I have is I I constantly see this dissonance between applications and the deployment of computing. And this is one of the reasons why we started Quantum Brilliance, which is people talk about applications. Uh, Intrinsically, most of them require thousands of computers to actually service a market. And I see this dissonance between where other quantum computing technology is going and can it actually really service that application to those markets? Because if you do that, you need to have thousands of these devices. You can't just have a few precious ones or ones which are the size of football stadiums. So that is kind of one thing I'd love people to think more critically about, which is how do you actually take this application and service the market you're talking about? And what is then the requirements on the computing infrastructure that's required to do that? So that's my one that I constantly try to remind people about.
And just to wrap up, another maybe provocative statement, but what's the most overlooked application of quantum accelerators that's not being talked about yet? Because I think we're all getting bored of the same three these days.
It's hybrid computing sensing. So it is things like in communications, doing signal processing where you are sensing a radio or a microwave field, and you're also then performing signal processing on it in one step. And that is one of those applications where I don't see anyone except a very select few talking about it.
That's awesome. Well, thank you again, Marcus, for joining us on the podcast and telling us more about your approach. Definitely, a lot of us that have been in the field have heard about NV centers for a long time, but haven't really seen them coming into the conversation about quantum technologies yet. So, yeah, thanks again for joining us and talking about the work and the partnerships that you're doing. And for our listeners, if you enjoyed this episode, don't forget to like, subscribe if you're on YouTube watching this. Can drop any comments below. We will pass it on to the Quantum Brilliance team and maybe have them back as well. And remember to share this episode. So we will see you next time on the Quantum State, where we decode the future of quantum computing.